Hi, my name is Emma, and today we're going to be talking about hemoglobin, and specifically the heme group and how oxygen binds to that heme group. So, in this first slide, you can see I have hemoglobin on the left and the heme group on the right. Hemoglobin is an oxygen-carrying molecule, and it delivers oxygen throughout the body. And hemoglobin has 4 heme groups because of the 4 subunits containing one heme group. So oxygen has the ability to bind 4 different oxygens when in the lungs. So where does oxygen bind? Oxygen is going to bind to the 6th coordination site of the iron ion in the heme group. And as you can see here, the binding of oxygen does change the conformation of the heme group. So what does the binding of oxygen do to the heme group? It rearranges the electrons within the iron, and this causes the iron to become smaller, and when it is smaller, it can move into the plane of the porphyrin. And as we can see in the picture here, the iron atom is big before oxygen is binded to it, so it is out of the plane. And when oxygen binds, it is going to be moved up because the iron ion is now smaller and it can fit well into the plane. So this structural conformation does have a big effect on hemoglobin. So the binding of O2 causes structural changes, so it would disrupt the bonds between the subunits of hemoglobin, which actually is good because then these disrupted bonds will cause a higher affinity of O2 in the remaining subunits. So in the lungs, when oxygen is trying to bind to hemoglobin so it can be transported, when one O2 binds to a hemoglobin subunit, the other subunits in that hemoglobin are going to have a higher affinity for oxygen, so the bonding is going to happen at a rapid pace. So what is the binding capacity of oxygen to heme in the lungs? So due to partial pressures of gases, temperature, and pH affect binding capacity of hemoglobin, specifically oxygen to the heme group. In the lungs, there is high pressure of O2 because you're breathing in oxygen, and there's a low temperature and a low pH. But the pH that's in the lungs is higher than in the tissue. It's about like 7.3 to 7.4. And these conditions ultimately help oxygen to bind to the heme group. So in the lungs, hemoglobin is saturated with O2, as 98% of oxygen binding sites are occupied on heme groups. So this is really important because oxygen binding needs to happen in the lungs so that it can be transported to the body. And then in the capillaries, the oxygen is going to be released. So an overview slide, when PO2 is high, which it is in the pulmonary capillaries or the lungs, oxygen binds with the hemoglobin. When PO2 is low, as in the tissue capillaries, O2 is released from the hemoglobin. This is ultimately causing oxygen to dissociate and mix with the blood. So I go more into detail on this next slide. So there's a relationship with pH and carbon dioxide. So once the red blood cells move through the body and get into the tissues, the carbon dioxide levels are going to go up. And when carbon dioxide goes up, levels go up, the pH is going to go down because there's a higher concentration of H+ ions and amino acid residues. So in this picture, on the bottom right of the slide, we can see the reaction happening. CO2 from the body tissue is going into the red blood cells, and that is causing the carbon dioxide to react with water. And when that goes through, the reaction happens a carbonic anhydrase, and it forms an intermediate H2CO3, which then goes to CHCO3 negative minus plus H+. So this is causing some ions to form in the body, and it's going to cause a lower pH. So also, CO2 is known to be acidic, so when it interacts with water, the pH of capillaries will decrease and the O2 will be released from the heme groups. This occurs because the greater the H+ ion concentration, various amino acid residues, such as histidine, stabilizes the deoxyhemoglobin in the T state. And the T state is when the oxygen is no longer bound to the heme groups. The T state has a lower affinity for oxygen than the R state. So with an increased acidity, such as in the capillaries and the tissues, the hemoglobin binds less O2, and ultimately this is known as the Bohr effect. So that is why when hemoglobin is in the lungs, oxygen is going to bind because there's a higher pH there and more fit environments. There's a higher concentration of O2, a lower concentration of CO2, so that oxygen is going to bind. The hemoglobin is going to be oxygen loving, and then it's going to be moving through the body. And once the hemoglobin moves through the body, there's going to be a lower concentration of O2, but a higher concentration of CO2, which is going to cause a lower pH. And when hemoglobin is in a lower pH, the O2 groups are going to disassociate because there's a reversible bond between O2 and the heme groups, which is going to cause the oxygen to flow into the blood, and it's going to create our T state hemoglobin, and the T state hemoglobin is not going to bind O2 again until it's back into the lungs. So basically, this is an overview of hemoglobin and oxygen and how it all binds to the heme group. So thank you. I hope you learned something, and I look forward to hearing your feedback.